The kinds of things that you would want to make sure that are secured include anything from your own personal contacts and your own credit card payment information to information from your company, intellectual property from the company, healthcare data, all sorts of things like this. So the thing here is that the requirements are fairly similar whether you are a consumer or whether you're a company. And so a lot of the security features that I'm going to be talking to you about today apply to both consumer devices and to enterprise devices. And so it'll give you a thorough background on how to answer questions from customers around why is Android secure and why should we trust it. There are going to be some cases where the features I'm going to talk about are specific to enterprise, and I'll call those out. And then there are a couple things that are actually consumer only, and I'll mention those as well. So the types of threats that we look at, we sort of break them into three different groups when we talk about threats to a mobile device. So the first one is user type threats, where either someone steals a user's device, or the user maybe loses a device, or maybe the user doesn't have a good password, and they might be able to get in and have their device compromised that way. The second one is app-based threats. So malware that might get installed from some sort of a mechanism that might attempt to compromise the device, from an app perspective. And then the third one is platform-based vulnerabilities. So maybe vulnerabilities in the operating system itself, and kind of what are the mitigations there around the types of things that we build into the operating system, the types of security updates, et cetera, that we build. So when you combine all three of these types of threats together, this is kind of how we think of the layers of security within Android. So first I'm going to start off talking about the user type threats. So first we'll start talking about the lock screen. So the user has a lock screen on it, and this is the first number one thing that a user has to do to start to secure their device. And it's actually surprising to me how many of my friends don't have a lock screen on their phone, or how many of my family members don't have a lock screen on their phone. It's they're always like, well, what difference does it make? What do I have on there? But typically, like, you have your banking data on there, all sorts of stuff that can be potentially that someone could get into. But the other thing is, if you don't even put a password on your device, someone can connect up a USB cable to it and get in through Android debug and copy everything completely off your device in general. So you really have to start with a lock screen. And the lock screen in Android is rate limited at this point. So that was something that was added a couple of versions back. So it starts to slow you down as you attempt to do password attempts. And then also you can work with an EMM, of course, to set a certain number of password attempts before it fails. What is recent or fairly new in lock screen management is that we now use hardware-backed key store in addition to the user's personal password. And so what we do is the PIN, password, or biometric information that the end user puts in for their lock screen gets converted to a random number string. And that actually gets combined with a key that is held within a hardware key store, and we're gonna talk about the hardware key store in a slide coming up. But the combination of both the password random string and the hardware-based key store are mixed together, and the two of those together are used and run through a password-based key derivation function, and that is what actually is used to create the encryption key for the device itself, for the encryption on the device. And so what this means is that if you are attempting to copy off the whole operating system or the whole user data space onto another computer and attempt to crack it, with a supercomputer or a iterative password guessing function, it's very, very difficult to do because you don't have the hardware-based key that gets matched with the user's key. And so this makes attempting to break through the encryption extremely difficult, even if you were to be able to download the encrypted user data. And so what we've added in 8 is that going beyond the hardware-based key that's stored within the trusted execution environment, we now have the capability to have a separate tamper-proof component on the device called a secure element. And the secure element is even further resistant to physical attacks. And so that makes it even more difficult to get on there and get the hardware-based key to unlock the personal password. I believe that Pixel is one of the first devices that supports the tamper-resistant hardware, but I think a lot of other devices are going to be joining with that as well. So let's talk about encryption and kind of what you need to know about encryption. So encryption's been available within Android from Android 3.0, but it was not required until after 5.0. So in 5.0, it was still optional, but if you used Android Enterprise, if you wanted Android Enterprise, you had to turn on encryption. So the important thing to know there is that when you're using 5.0 devices, which at this point are really old, but if you're using 5.0 devices, when you first start up Android Enterprise, you may have had to wait for the device to get encrypted. And you may have found that you needed to plug the device in and get it fully charged before it would even begin the encryption process. So in 6.0, we made it so that devices had to be encrypted out of the box. So it saved a lot of time because you didn't have to wait for the device to encrypt itself, and you didn't have to plug in the device and wait for it to charge. In Android 7, we added the concept of file-based encryption as opposed to full disk encryption. So full disk encryption, the entire user space data is encrypted with one encryption key. And that encryption key, as I mentioned, is derived from your user PIN and the hardware-based key. Now, in Android 7, file-based encryption, now you have more than one encryption key. You have an encryption key for the work profile, you have an encryption key for the personal profile, and you have a third encryption key for the operating system itself. And so what this means is that the device can boot and start running the basic functions of the operating system before you put in any keys at all. But it can't get access to the user's data, and you can't get access to the work profile data. Now, file-based encryption is still an optional capability, so not all devices support file-based encryption yet, but it is a capability that's there. And then the base encryption was AES 128, but you can do AES 256 or higher if your processor supports it in terms of enough power and throughput on the device. And again, that's something that's also OEM dependent. So in a lot of these cases, I'm going to talk about things that might be called optional versus things that might be mandatory within Android Enterprise. And the reason for that is that everyone's familiar with the compatibility definition document that Google puts out. They basically put out a specification for what you can do within Android, but some things are mandatory and some things are optional because they want to make it as easy as possible for OEMs to comply and not make things too difficult. So sometimes things are mandatory and sometimes they're optional. Now, in version 8, we also added key ejection, which what this means is that the encryption key that is used for the work profile or for the personal profile gets physically removed from memory when you press the lock button. And so this also makes it more difficult for someone to be able to copy down the entire memory space and look for the encryption key in a device that's turned on. So it's one more layer of things that make it more difficult to get into an encrypted device. Okay, so let's talk about how we prevent or how we protect encryption keys and how we prevent devices from being physically attacked. So first, I want to talk about trusted execution environments. So the most common trusted execution environment is something from Qualcomm called Trust Zone, and it is a separate virtualized space on the system on a chip, generally the Snapdragon chip or an equivalent chip that cannot be accessed at the same time that the operating system is running. So it physically has power pins that turn on the device when the operating system turns off. So it can only be running Trust Zone or running Android, but never running both of them at the same time. So they're physically separated from each other. And inside the trusted execution environment, it runs a small special operating system, a Trust Zone OS, and all it does is encryption operations and key operations. And so the operating system itself sends messages into the Trust Zone to do an encryption or do a decryption, and then it turns over control completely. And so when we say hardware-based key storage, hardware keys, encryption keys are stored inside this trusted execution environment and cannot be accessed at all from Android or from the Linux OS because they're physically separated. And so we talked about the PIN verification process. I talked about how you mix the personal key and the hardware key. Going beyond that, we've added some new things in Android recently, one of which is version binding. So we have it set up so that if you have a set of keys that are within the trusted execution environment being stored there, it also stores the version of the operating system inside the trusted execution environment so that if you attempt to downgrade the OS, it will invalidate all the keys that are being stored there. And so what we don't want to have happen is we don't want you to downgrade the OS to a certain point where you could find a vulnerability and then use it to break into the trusted execution environment and get the keys. So we invalidate the keys if you downgrade the OS. And then rollback prevention is a very similar protection, but this actually keeps a copy. It uses the same copy of the operating system version in there, and it doesn't let you roll back the operating system at all. It won't let you downgrade, because a common type of attack method would be to roll back a few versions of the OS till you found one that supported the vulnerability that you're trying to use to attack with, and then you could go after the device. So this is another mechanism that's there. And then tamper-resistant hardware, we talked about it a bit, but it's a separate physical chip that is resistant to physical attacks, resistant to delaminating the chip. It's resistant to side channel attacks, electrical monitoring, electromagnetic monitoring, et cetera. And this is now something that we call that, in that case, a secure element. And the secure element is only accessed by the trusted execution environment. And so you can then store your keys inside the secure element and store the trusted execution environment OS inside the TEE, and then it gives it an even more secure place to hold the keys and make it even more tamper resistant. So another protection that we have, and this one's actually consumer focused, is called Find My Device. So this is a very basic one. You can just log in with your Google account as a consumer and just be able to go in there and find your device, locate, lock, or ring your device, and it'll show you your last known location or what the last known Wi-Fi was that it was on. So this one is pretty much consumer, and if you have an EMM of any kind, what you're going to have is a lot more powerful than this. but this basic functionality is available for consumers. So now I'm going to shift gears and talk about enterprise data and what we do to protect the device from app-based threats. So the first thing here is what we call Google Play Protect. So Google Play Protect is built into every device. It's part of what we call Google Play services. Now, every Android enterprise device has to be running Google Play services because Google Play is the mechanism through which we bring all the apps down onto the device. It's the mechanism through which you get the managed Google Play Store that we're going to hear about in more detail tomorrow. But what Google Play Protect is it's a set of application scanning and anti-malware scanning services that are on the device. And what it does is it scans all the apps either daily or every other day and looks for apps that are thought to be or known to be malware. And it can either warn the user upon attempted installation, or it can actually even remove apps that are thought to be malware after the fact. And we're going to dig into this a little bit more. So how does the application review process work within the context of Google Play? So when an app developer is looking to upload an app into Google Play for the first time, they have to create an account on the Google Play developer website, and within that account, they have to log in with generally a Gmail account or some sort of an account there. And so the first thing that Google knows about them is what account they logged in as. The second thing that they get is that apps have to get signed with a key as they get uploaded into Google's Play Store. And so at that point, you have two pieces of identification that you know the developer. And then we take the app, and the app gets reviewed through an automated process and then through a personal review process. And let me walk through what those mechanisms are. So static analysis is when they're reviewing the actual code itself. They're reviewing the code for improper coding practices, use of improper encryption algorithms, potentially SDKs that might have malware in them, and then also pieces of code that we may have seen before that are similar to code that we've found in malware. So this is actually this particular part is what we call static analysis. The second part that we do is dynamic analysis, where the app is actually run either in an emulator or run on a live device, or potentially both, looking for app behaviors. At that point, we're looking for behaviors maybe that change over time, et cetera, or behaviors that happen initially. And then from there, heuristic and similarity analysis. This gets into where artificial intelligence fits into the Google Play Protect analysis. But what we're looking for is behaviors out of this app that are similar to behaviors that we've seen before. So when this app runs, does it make your device get warm? Is it running cryptocurrency mining software? When this device gets run, the camera turns on. When this device gets run, what are the behaviors that are happening, and what are the effects that are happening on the device when this app gets run? And so there are a number of measurements that get taken, and you measure it for similar behavior. And then at this point, you can measure it against other apps that we've seen before, and see that maybe this app was built using the same type of malware that we've seen before. And this is where, I'll show you in a moment, but artificial intelligence fits in as well. So signatures. So as I was mentioning, this is really about the identity of the app developer. So If a developer is signed with a key that we've seen before, we know about that developer. And if the developer is logged in with an account that we've seen before, we know about that. And then if any apps are found to be malware in the future, we can not only take down that app, but we can take down every app that that developer has created if necessary, right? And then safety net is a number of different measurement capabilities that we have on the device that works together with heuristic and similarity analysis in order to be able to measure how the device is behaving over time. So it's able to kind of measure whether it's behaving badly or not. And I'm going to talk about a safety net on a slide coming up. And then third-party reports. The Google Play review process actually licenses third parties, other anti-malware companies, independent researchers, et cetera, in order to get those reports and be able to basically, at that point, you put everything together and it goes through a scoring engine. And if it is approved, then it's able to go through and get up there onto the Play Store. If it looks strange in any manner, then it goes through human review and it can get rejected. And apps get rejected constantly from the Play Store. Now, what happens when the device either gets approved or the app either gets approved or rejected is we then take a hash of that app, of the APK. So we have a unique fingerprint that represents what that app looks like. And then whenever the user is trying to download an app onto the device itself, we can compare the hash against the known database of apps that we now have up there in the cloud within Google Play Protect. And that database in the cloud is billions and billions of apps now because we scan like 2 billion devices a day, and there's 70 to 100 apps on each device. So we have a very, very large database of apps that are known to be good and bad. And the interesting thing about the Google Play Protect process as well, I think, is that it can scan apps whether they come down from the Google Play Store or whether they come from an external source that is not the Google Play Store. So even if a user chooses to sideload an app, it still has the capability of being scanned by Google Play Protect. And from an EMM perspective, one of the interesting and important things to remember is that you have two controls as an EMM. You can force the user, if they're using Android Enterprise, you can force them to only download apps from the Play Store and not use unknown sources. That's a very strong and powerful capability for protection for the users. The other thing that you can do is you can enforce that verify apps is turned on the device. So the combination of those two things, prevent users from downloading apps from other locations, and then ensuring that verify apps is turned on, in combination, that's a very powerful protection for the users when they're trying not to get bad apps on their device. So this is a picture of the artificial intelligence map or a version of it that's created by Google Play Protect as it's going through and analyzing some of the apps. So you can see what's interesting about this is it's showing you the types of malware that we find as apps get uploaded into the Play Store. They get rejected when we find these kinds of things. But it also it shows you how they can kind of compare similarity from one app to another and say that, you know, this device resembles something that we've seen before that's a Trojan, et cetera. So the artificial intelligence capabilities of Google Play Protect have been around for a couple of years now and are getting more powerful over time as they get more apps that they can see, that they can add to the database. So overall, with all these capabilities within Google Play Protect, you know, what does it mean in terms of the general safety of apps and devices? And, you know, what does it mean in terms of, you know, how well protected is the user? If you look at the blue line on the bottom, you can see that these are apps that have been downloaded only from the Google Play Store. So from the Google Play Store, if you only download apps from the Google Play Store, your chance of infection with anything that would resemble a potentially harmful app. Now, we don't call it necessarily malware. We call it a potentially harmful app because it's anything that Google doesn't like or thinks might look bad. It's not necessarily a rooting app or something that's really bad, but your chances of getting a potentially harmful app are less than 0.01%. Now, the green line is when you're downloading apps from unknown sources, and you could see that the percentage of potentially harmful apps is much higher outside unknown sources or outside the Play Store when downloading from unknown sources. And so this is one of the things that we tell customers is that we really highly recommend you only get your apps from the Google Play Store. And part of Android Enterprise, downloading apps from the managed Play Store, the only way that apps can get into the work profile or onto a fully managed device is from the managed Google Play Store. And so right there, that takes your risk of getting malware down extremely significantly compared to other sources. And so the anecdote now is that you're less likely to get a piece of malware than you are to get struck by lightning. So that's pretty amazing improvement over time, and it shows the commitment that Google has to scanning apps and making the Play Store a safe place to get apps. Now, the interesting thing here is that a lot of customers come back and say that it's their impression that iOS doesn't have as much malware. But the fact is that iOS has actually been growing in vulnerabilities and growing in malware as a percentage. And in some cases, there are more vulnerabilities and malware on iOS, versus Android, just because it's a big target, and hackers are going after iOS as well. And so that's one thing that we like to point out to customers, that Android is actually as secure, if not more secure in a lot of ways than iOS at this point. So how can you validate that your device is secure? What kinds of things can you do there? And this is where we use what we referred to as safety net on the previous slide. So the first thing that we have here is what we call safety net attestation. So this is, as I mentioned before, safety net uses a number of measurement capabilities within the device to measure whether the device has been rooted or changed in any way. And so what we have here is an API that an EMM can use or an app can use to basically take a measurement of the device, send it up to the cloud, to Google's safety net in the cloud, and basically request a response back as to, has this device been rooted before, or is this device in substantially the same condition as when it was originally tested by Google for compatibility. And so companies use this, ISVs use this capability in a number of different ways. But for example, Android Pay, the credit card app, calls the safety net attestation API before the app runs in order to verify that it has not been rooted, and it will not launch the app if safety net returns an answer that says it's been rooted. Now, the way this works actually is that you can't just return the answer back to the device, because if you return the answer back to the device and the device has been compromised, it'll just throw away the answer and ignore it, right? So generally you ask the cloud whether the device has been rooted. The cloud responds back to some other server somewhere else, and the server somewhere else responds back to Google Pay in that case and says, yes, this device is okay. It's okay to start the transaction in that case. Another example is Pokemon also uses this API because they don't want people to steal Pokecoins or whatever it is, be able to grab all of the monsters without by using a device that's been compromised. So It's also possible to use this as an EMM. So say you wanted to verify that the device has not been rooted before installing Android Enterprise the first time, or before installing a work profile, you could call this API. And some of our EMM partners are doing this at this time. The second component within SafetyNet is safe browsing. So this uses all the capabilities of Google's web crawling engine to make a list of basically known bad websites, whether they be phishing websites or malware, etc. But if you get to a bad site, it pops up a big red blocking message on the device, and highly discourages users from going to that. In fact, SafetyNet safe browsing is so effective that other browsers license this technology from Google. So you would be able to see these types of messages on other browsers as well. And then reCAPTCHA software, you've seen that. It's the thing that asks you if you're not a robot when you're going in to do a transaction on a website. And then SafetyNet Verify Apps is actually the name of the component that helps to scan the apps and build and compare the hash codes for the apps. So all of these capabilities together go towards verifying in real time that the device has not been tampered with. So let's talk about process isolation, how we separate one app from another within the operating system, and how we keep one app from tampering with another app once it's been installed on the device. So we have the concept of application sandboxing. And the way application sandboxing works within Android is built on top of Linux, actually built on top of SE Linux, which we'll talk about in another slide. But every process, as it gets installed from outside the device, gets installed with its own user ID within Linux. So if you're familiar with Linux and the login, you log in, you are one user, you have your own directory, you have your own data space, everything, you can only see your own space. Now, every app that gets installed as its own user, it gets its own data space. It looks like it's the only app installed on the entire system as far as it's concerned. It can't write to any other apps' data directories. It can't communicate with any other apps at all. The only way that it can communicate with another app is by sending what we call an intent to the operating system. An intent basically says, I want to access a browser. I have this URL. Operating system, can you help me find a browser? And so the operating system will say, okay, I'll take that URL and I'll send it to a registered browser somewhere on the system. And so that is the only way that an app in general can communicate with another app, is by sending an intent through the operating system. Now, the work profile goes one step further and is able to separate the work apps from the personal apps by using UDIDs that are separate from the personal devices. So all of the personal apps, their UDIDs start with a 0. And all the work apps, their UDIDs start with a 1. So it's very easy to filter user 0 apps from user 1 apps. It's a extremely easy just filtering mechanism. So by default, work apps cannot send any intents to personal apps, and vice versa, unless you have enabled it via the EMM. Now, there are some exceptions that we've had to make within the operating system to make things just run a little bit better. Like, for example, the contacts app within the work profile wouldn't be able to access the phone dialer because it's on the personal profile. So we have to set up some situations where you can pass some data from the work to the personal. But in general, they're completely separated. And the separation is so complete that, for example, when you have an EMM that is installed that's controlling the work profile, that EMM actually lives within the work profile and cannot access and cannot view the apps that are on in the personal profile. So that just demonstrates kind of how complete that isolation is. So moving on to platform-based threats and how we mitigate those. So in general, the philosophy here is that we look for places within the Android operating system and within the SE Linux kernel below, we look for places where we can reduce the attack surface to make it more difficult to come up with a vulnerability that could give you complete control over the device. And so that's what we've been doing over the course of several years, is hardening the OS by reducing the attack surface. So the first thing we did is Android is built on top of SE Linux. This is security enhanced Linux. This is a version of Linux that basically breaks the operating system down into a whole bunch of different domains, and so only apps only apps that are that have the correct privileges can execute any functions at all, and they can only execute it within the domain that they're allowed to do that. So SE Linux introduces what we call mandatory access control as opposed to discretionary access control. So if you're familiar with Linux in general, discretionary access control is you get privileges if you're an app. You basically can see other apps and see other files based on read, write, and execute. Right? That's how kind of the file system works within regular Linux. But SE Linux adds another layer, what we call mandatory access control, where there's actually a policy file, and every time an app is attempting to do anything, or in fact, anytime a piece of the operating system itself is attempting to do a task, it has to look it up in the policy file and find out if there is a rule in the policy file that says that this component or this app can do a certain function, and if it doesn't have privileges for that, it stops it basically, regardless of whether it had read, write, or execute privileges. So, for example, root. If you get root access in Linux, generally what that means is that you have access to the entire operating system. You can read or write any file anywhere in the operating system. But within SE Linux, that's not the case. Root only has access to certain domains, and it cannot go and be able to access any aspect of the operating system. So it confines a process within the domain that it's supposed to be running in. So this capability by itself reduces the attack surface that a vulnerability can get, so that it can't do much damage if it were able to get into the operating system. So what additional kernel hardening capabilities do we have, and what other things have we been doing over time? So all of these capabilities here that we talk about are examples of other things that we've done to harden the operating system. So first I'll talk about kernel address space layout randomization. So we came up with regular address space layout randomization a couple versions ago within Android, and what it basically means is that every time an app gets loaded, it's going to get loaded into a different spot within the operating system, a random place. And what this helps with is that if you found, for example, a memory buffer overflow, or some sort of a location-based attack where you can try to jump to another part of memory and start executing code, that wouldn't work anymore, because every time your app gets loaded, it gets loaded into another spot, a different spot in memory. So we've had address space layout randomization for a while. Now we also have kernel address space layout randomization, which means even the kernel gets loaded in a random fashion so that the kernel components are not next to each other. So it makes it very difficult to have an attack that works more than once. And then position-independent executables go along with address space layout randomization, because we require that apps that you write be able to be loaded in any space in memory. For example, they can't ask for a specific memory location. They must be independent. Fortify source is another type of kernel hardening, and this is a set of libraries that you could use at compile time and testing time to verify that you're not having memory buffer overflows, etc. Extra capabilities. SecComp is a what they call SecComp filtering. Is there are many ports within Linux, right? That's how it communicates. But SecComp shuts down all ports that are not being used by Android, and so it shuts down like 90% of the ports. And so you can't go attack ports that are unused because they've been shut off. And then Project Treble, I've got a couple of slides on it because it's worth discussing in more detail in its own. This was a change in the operating system that we started in Android 8, where the firmware used to be separated from the OS, or the firmware used to communicate directly to the OS. And the firmware is the code, for example, that handles the camera and the speakers and the video drivers, etc. What we found was that folks might remember the stage fright vulnerability. It was a vulnerability in the media handling software within Android. And so what we found is that someone found a vulnerability within the firmware for the media handler and was able to jump into the operating system and completely take over the operating system. Now, we patched that immediately, but we figured out that that's really a bad idea to let something that's in the firmware jump back into the operating system and be able to do whatever they wanted. So we created a hardware abstraction layer that the firmware now can only talk to the hardware abstraction layer, and the hardware abstraction layer now can only talk to the OS. And so we've separated that to be able to isolate problems in the OS jumping into the firmware, and vice versa, problems in the firmware jumping into the OS. So this is a slightly more complicated architectural diagram of what's going on here, but it used to be that any driver could access any HAL within the system, but we've also further optimized it so that a single driver within a kernel, every single one of them gets their own HAL, and so they can only speak with their own hardware abstraction layer. And this combination really makes it quite difficult for a vulnerability that's found within any of the drivers to get back up into the operating system. And so the side effect is that this actually makes it much easier for operating system vendors to upgrade the OS from one major version of Android to another, because they don't have to rewrite all the drivers to go from Android 8 to Android 9, for example. All the drivers are generally independent from the operating system itself, which sits above the hardware abstraction layer. So the interesting thing here is that when we announced Android P, we had, I think it was 8 or 9 device manufacturers on stage with us that had Android P on day one, because it was so easy to port from Android Oreo to Android P because of Project Treble. So that's something that's really helped out a lot, and we hope it will make it easier for operating system updates going forward in the future as well, because you don't have to modify the kernel drivers. The next thing I want to talk about is verified boot. So this is actually something that was partially there in Android in the beginning, but it was something that Android learned and borrowed technology from Chrome OS. So Chrome OS has always had verified boot, but basically what it is it's cryptographic verification of the boot components. As you first turn on the device, the way the device boots is it loads a very small set of code called the bootloader, and then it starts to load additional components one by one off of basically separate memory spaces until it gets to the operating system itself. And what verified boot does is it takes a cryptographic hash of each component from the bootloader on and verifies that with the key that's stored in the trusted execution environment before it loads any of those components. And so if it gets to the point where it verifies against those keys and it finds that anything has been tampered with, it it can fail to boot and end up going back to rebooting or just failing to boot. Now, the other part that was added within verified boot is the concept of AB operating system updates. So 2 different versions of the operating system. So if one of the versions gets corrupted, it can revert back to the previous version that was the one that was installed before. So it has benefits when you're downloading the OS. You can download the OS kind of in the background, and you can also use it as a kind of fallback OS if verified boot fails. And so we use a locked bootloader. That's another option that OEMs have. And if the bootloader is unlocked, then that's when you can swap out the boot code, etc. But if you were to unlock the bootloader in order to change any of the boot code, that automatically wipes the user's personal data. It wipes out the whole user space. And so the combination of verified boot, locked bootloader, etc., protects the operating system boot stage from tampering. Now let's talk about protections for data in motion. So a number of these are new, actually. We do have VPN capabilities. So we're going to learn about these a little bit more tomorrow. But there is the capability of having a VPN for the work profile. It's different from the VPN from the personal profile, and this is there to protect data while it's in transit. And all devices actually are required to implement TLS encryption by default. So apps, in fact, that get installed, apps have to communicate to their back end using TLS encrypted communications. And if they don't do that by default, they can get rejected from the Play Store as they're looking to be accepted. And then there are a couple of components, preloaded trust anchors and leaf pinning, that relate to the certificates that are used by the devices. So trust anchors are root certificates or root certificate authorities, and those are all loaded on the device by the operating system itself. And we've made it more difficult now by default for apps to trust other certificates. By default, apps are only going to trust the certificates that are installed by default on the OS, unless your app specifically says, I want to trust a separate certificate. So that makes it more difficult for an extra root certificate to get installed on the device and the device to get man-in-the-middle attacks. And so that's kind of what we've done there with trust anchors and leaf pinning. So overall, with all these capabilities that we have for taking vulnerabilities and mitigating them with all these kernel hardening mechanisms, how well has that helped us to protect against vulnerabilities? Well, what I want to point out here is that there were quite a few very scary vulnerabilities that were in the press. And when it turned out, when it first came out in the press, the story was, billions of devices are vulnerable. 95% of the devices were vulnerable to stage fright, for example. But Google patched the vulnerabilities within less than weeks, and those vulnerabilities were patched, and the updates were made available to the Android open source program really before the announcement was even made publicly. And we found that there were actually no public exploits of stage fright, for example. Even though billions of devices were potentially vulnerable, none of them were actually confirmed. And we've yet to see, even today, we've yet to see any confirmed exploits, for example, of stage fright. And so the point here on this slide is that if all you did was read articles about how scary it is on Android, you would not have a complete picture, because the fact is Android is much more secure than the press would have you believe. Perception the perception of Android security is not reality. The reality is Android is much more secure than you would believe. And so now I want to talk about some of the things that we're doing working with the ecosystem to continue to keep Android secure going forward. So working with device manufacturers on the operating system based protections that we've talked about, working with system on a chip vendors. This is where we're working with like the trusted execution environment, et cetera. Working with mobile operators. We've been cooperating with mobile operators now for quite some time to get them to come out quickly with operating system security updates so that they didn't wait too long, and to be able to separate the concept of a security update from a full OS update so that they can bring out the security updates more quickly. And then we work with academic institutions, independent security researchers, and the Linux community, and we actually pay money for vulnerabilities that are brought to our attention. And so we work together with all these players in the industry to keep Android secure. And how have we been doing in that area? Well, what this is showing is that it's getting more expensive now to buy an exploit for Android. For example, we pay out rewards, and Android has to pay more money for a vulnerability in some cases than iOS. And we believe that's an indication that it's harder to build an exploit now for Android than it is for iOS. And you can see the mobile pwn-to-own competition in 2016 and 2017. We have to pay out more money at the mobile pwn-to-own competition for exploits. And it's very interesting to note that in 2017, the Pixel, which was running at that time Android Oreo with the secure element, it was one of the only devices that was not compromised at all. Our competitor OS was actually compromised. And so that's a very strong endorsement for the improvements that we've made in security over the last several years. So I do a lot of security briefings for customers, and after presenting all this evidence along with all of the information that we have on the security architecture, pretty much every single customer comes away having learned a lot about security and having really changed their whole perception of Android security. And so what I'm hoping to do here today is arm you with that same data, the same slide deck, the same capabilities here and knowledge around Android security so that you can go and be able to make these presentations. Hopefully that will be valuable.